Hi, I'm Dave Ballo, an RF application engineer at Keysight Technologies. In this video, I'll show you an exciting new option for high-performance spectrum analysis that complements the current suite of Pna measurements. I'm standing next to a Pna network analyzer with a simple single-stage RF down converter. I'm measuring conversion gain, intermodulation distortion, gain compression, and noise figure. And this is all being done with a single set of connections to the converter. These measurements can be performed many times faster compared to those done with the traditional approach using a spectrum analyzer and standalone signal generators. However, a spectrum analyzer remains an essential tool to measure undesired spurious signals coming from the converter. The new Pna option adds fast spur search capability to the Pna-X, replacing a standalone spectrum analyzer and switch matrix in your test systems. Spurious measurements are a very important part of characterizing frequency converters, but they often take a great deal of time. With the new spectrum analyzer option, a Pna-X can quickly perform spurious searches across a broad frequency range with measurements that are as fast or often faster than those from today's best standalone spectrum analyzers. Let's take a look at the Pna spectrum analyzer in action. In this window, I'm performing a narrow frequency sweep with a fixed LO to look at gain and group delay in the passband, and a wider sweep to look at stop band performance. In this window, I can quickly measure gain compression versus frequency, and in this window, I'm measuring swept intermodulation distortion performance. So far, so good. However, in my noise figure measurement, I'm getting an error message indicating compression in the noise receiver. This indicates that there is either too much noise power or a spurious signal that is overloading the noise receiver, which can cause bad measurements. This condition often occurs when measuring high-gain devices with an incorrect test setup. However, this frequency converter only has 8 dB of gain, so it can't be overdriving the noise receiver. A spectrum analyzer would be very useful in this case to determine if an out-of-band signal was causing the overload. Taking advantage of a feature called Marker to SA, I can place a marker in the passband of the converter and open a spectrum analyzer channel that has the same stimulus conditions as those used in the noise figure channel. Now we see the output signal at 880 MHz with a 50 MHz span. Notice as I decrease the resolution bandwidth setting, I can maintain excellent sweep speed while improving measurement sensitivity. Since I suspect that LO feed-through at 2.2 GHz is causing the compression of the noise receiver, I will set the stop frequency of the spectrum measurement to 4 GHz. Sure enough, I can see that the LO feed-through is very strong, about -25 dBm, and it remains fixed as the input power is dropped. That level of LO leakage is definitely too large for the noise receiver. It looks like there are other spurious signals coming out of the converter, so I'll press the full span soft key to look further out in frequency. Now I see the full range of spurious products coming out of the converter. I can also add measurements at the input and LO ports of the DUT by simply adding measurements using the test receivers at ports 1 and 3. The A receiver at port 1 shows the spurious signals coming out the input port, which, if connected to an antenna, could cause radio frequency interference. The C receiver at port 3 shows the large amount of spurious products coming out of the converter's LO port, which in this case is to be expected since there are no LO amplifiers to provide reverse isolation. This multi-port spectrum analysis capability very quickly gives you lots of insights into the operation of your converter and cannot easily be achieved in any other way. I just happen to have a 1.2 gigahertz low-pass filter, which I'll add to the output of the converter. This filter does a great job of removing the spurious signals and allows me to make my noise figure measurements free of noise receiver compression. Zooming in with the spectrum analyzer, I see the LO feed-through has been knocked down to -85 dBm. Now, let's take a look at the fixed IF response of the converter, which is used to measure the front-end bandwidth. This response is generated by sweeping both the input and LO signals to the converter. This trace shows that at 2.64 gigahertz, there's a glitch that changes from sweep to sweep. These are usually caused by spurious signals landing at the same frequency as the desired signal, adding in and out of phase. Using the marker to SA feature again, I can open a new window with a new spectrum analyzer channel. Again, I see a fixed output signal. Next, I'll set the input and LO signals to sweep, which creates a fixed IF measurement. Now the spectrum display shows a crossing spur that interferes with the desired output signal, causing the glitch on the fixed IF conversion trace. Observing how fast the crossing spur moves can help provide insight into its polynomial order, helping diagnose the problem. All of the spectrum analysis measurements can be performed with calibration, which removes cable losses and corrects the frequency responses of the measurement receivers. If the measurement is performed on a device in a fixture or measured on wafer, de-embedding and port power compensation can be applied to extend the calibration planes directly to the input and output pins or pads of the device. All of this gives high levels of amplitude accuracy when measuring spurious signals, ensuring you know exactly how your converter is performing. Keysight's new Pna spectrum analyzer option lets you make high-performance spectrum and network analyzer measurements with a single instrument, enabling unrivaled insight into your devices. A Pna X-based solution can dramatically improve the test throughput compared to traditional converter test systems. For more information about the Pna family and the spectrum analyzer option, visit us at the link shown on the screen. Thanks for watching.